Alright, so here we are, final lesson in this unit about writing exponential and power functions. Remember, exponential functions are those ones that have the exponent, that's the variable. Power functions kind of the reverse of that. You have a variable for the base and then you're raising it to some sort of exponent. Yeah, it should be pretty easy, right? So just one objective here. Let's look at the objective slide. Being able to write exponential and power functions. And so the image there is taken from a joke t-shirt. Exponential growth, it's as easy as 1, 2, 4. Well, somebody doesn't know how to count, right? Except they do. So what this is saying, this is basically the equation y is equal to 2 to the x, because 2 to the 0 power is 1, 2 to the first power is 2, and 2 to the second power is 4. Exponential growth. That's what we're doing, but except for we're going to be given a collection of points, and we're supposed to come up with the equation that goes with it. Okay, so let's review what exponential function looks like. In general, it looks like this. Y is equal to a, that's not the base, this is the what it's scaled by, a times b, that is the base, raised to the x power. So the a, it's not 0. If it was 0, then we just have y is equal to 0. That's silly. Okay, and your b, your base, got to be a positive number, and it can't be 1. All right, so notice that in that equation, you have an a, you have a b, you have 2 parameters, right? You have only 2 parameters, so let me ask you, if you've got 2 parameters, how many equations do you need in order to solve it? How many points do you need? Well, if you need if you're trying to find 2 parameters, you need 2 points so that you can write 2 equations. It's basically a system of equations that you're going to have to solve. When you solve this system, you're not solving it by like elimination or matrices. We're just going to use the classic substitution method to solve this. Take a look. So on this first exercise, find the exponential function that passes through these 2 points, 1, 2, and 350. So let's first write down what our equation is supposed to look like. Y equals a times our base raised to the x power. And we're going to solve this thing by substitution. Okay, so now just plug in the points. 1 in for x and 2 in for y. So 2 is equal to a times b to the 1 power. Okay, and then the second one, 3 in for x and 50 in for y. 50 equals a times b to the 3rd power. So since we're solving this by substitution, what this means is that you solve for one of the variables, take that expression, and put it into the other equation. You always want to choose the simpler one, so that's going to be the first one here. Solve it for a. So a is going to be equal to, just divide the b over there, 2 divided by b. Now I'm going to take that expression and substitute it in for a in the second equation, and this is what I get. I get 50 is equal to a, not a, I'm taking the a out. I'm taking the a out. I'm going to get 2 divided by b, that's in the place of a, all of this times b to the 3rd. Now let me just keep simplifying the right hand side of this. That's 2b cubed over b, and then b cubed over b, we just subtract the exponents, so that's 2b squared. Get rid of your 2, that's the coefficient 2, by just dividing both sides, and we get 25 equals b squared. And now take the square root. So when I take the square root, I should technically get plus or minus 5. But we know the base has got to be a positive number, so it's not going to be negative 5, it's just positive 5. There we go. Now to get the a, just put that back into that first equation right here. A is equal to 2 divided by my b value, which is 5, 2/5. There we go. Put them both together. Don't make me do the work. You do the work. Put them both together, write our equation. Y is equal to my a value, which is 2/5, times my b value, which is 5 raised to the x power. Okay, and this is a piece of cake to check. Just plug in your points, see if they make sense. By plugging 1, 2 to the 5th is, or 5 to the 1st power is 5, times 2 to the 5th is, or 2/5 is 2. There we go. I said it was a piece of cake, but apparently I can't talk. How about we stick in 3? 5 to the 3rd power is 125. Times 2/5, well 5 goes into 125. 25 times, 2 times that is 50, so it does check out. All right, okay. So here are the steps involved in that. Just 5 simple little steps here. So here are the steps to write an exponential function if you're given 2 points. So the first one is to go ahead and substitute those points into the equation y equals a times b to the x. You're not sticking them for a and b. You're sticking them in for x and for y. And you're solving for a and b by substitution. So step 2, you're going to solve the simpler equation for a and then substitute that expression into the other equation in the place of a, and that gets rid of it. So then step 3, solve that new equation for b. Once you have that b value, then you're going to put it back into the original equations to solve for a. Now you have your a and your b value. Don't make me do the work, you do the work, and rewrite your equation y equals a times b to the x. Right? Maybe take a second or two to check it, make sure it makes sense. So here's a chance for you to try that, right? On exercise 2, find exponential function passes through those 2 points, 220 and 6, 320, go. Okay, let's check our work. Is this what you got? Y is equal to 5, it's the a value, times 2, which is the base, raised to the x power. Right, so we put our points into the equation, y equals a times b to the x. You put them in for x and for y. Solve that first one for a and substitute that expression in for a in the second equation. And then whenever you go to simplify right here, I subtract my exponents. When I subtract my exponents, b to the 6 divided by b to the second gives me b to the 4th. Divide by that 20. And then take the 4th root. Should be plus or minus, but you know, base got to be positive. And then finally find your a value. All right, so now I'm going to do something kind of strange. See if you can follow me here. So if you solve that correctly, you should have gotten y equals 5 times 2 to the x, and we did. Okay, so in your calculator, in your graphing calculator, you have one handy? Yes? Yes? Okay. I want you to graph. Well, go to y equals and type in this equation, the same equation that you just got. So you should get a graph like this, right? It's an exponential equation. The base is 2, and then we're scaling it by 5. Okay, then go back to y equals. Go to y2. Just scroll down to y2, and then type in natural log, so the ln, and inside the parentheses, put in y1. Where do you get the y1? y1 is from the vars menu. So you get a vars, you choose y vars, you choose function, and it should be right there, so y1. So put that in parentheses. What that's going to do is it's going to take the natural log of all the y values from the original equation. And let's see why we're going to do that. After you have that typed in, hit graph and see what kind of thing happens. Like, whoa, I get a straight line. That's crazy. I get a straight line whenever I graph x, comma, natural log of y. Now this is kind of a cheat here because whenever I'm graphing x, comma, the natural log of y, the y-axis is not a y-axis. The y-axis is actually a natural log of y. So in other words, the first one, the number 1, is the natural log of 1. Number 2 is the natural log of 2, and so on. Okay. So in general, if you have 2 or more points of data, x, comma, y, they're going to fit an exponential model if and only if the points x, comma, natural log of y fit a linear model. So this is exactly what we just saw in the previous question. So what this means is you have your set of data. If you find the natural log of y and you plot the points x, comma, natural log of y, if I get a line, then the original set of data must have been exponential. Okay? All right, so let's see why that's true. Let's see why that's true. Okay. So let's consider a very simple exponential function. Y is equal to 2 to the raised to the x power. All right, that's pretty simple. And now let's, oh, well, there's the graph for it. And now let's go ahead and take the natural log of both sides of that. So natural log of 1, what do I get to do with that exponent there? Using the power property, I get to bring that x out front, yes. Now, this is a linear equation in terms of x and the natural log of y. okay? Not in terms of x and y, which is what you're used to, but x and the natural log of y. So x, the x-axis will be the same, but the y-axis is now a natural log of y-axis. So here's this like in an approximated form, and you can see the number that is right in front of the x, the 0.69 is the natural log of 2, and that's the slope of the equation, okay? That's the slope of that equation. So look over here at the little graph, the second graph here. You can see that the x values stay the same on the x-axis, but the y-axis becomes the natural log of y. So the only reason why we're looking at this is that if I have a set of data, and I do this to the set of data, and if I get myself a straight line, I know that the original set of data was exponential, and I could go ahead and write myself an exponential function for it. Okay, so let me look at this in general now. So let's consider y equals a times b to the x, right? So just like we did before, take the natural log of both sides. On the right-hand side of that, I have a log of a product. So I can use the product property and expand that out as the natural log of a plus the natural log of b to the x. And then the exponent on b to the x gets to come out front, and then here is my new linear equation, right, where natural log of a is the y-intercept, and the natural log of b is the slope. So b is the base, and a is what we're scaling by. B is the base, and a is what we're scaling by. So let's take a look at that back on that the last problem that we just did. Okay, let's look at that on the last problem. So on this problem, let's just kind of eyeball where the slope and the y-intercept are. So if I look at this, I can see that my y-intercept, I'm going to say my y-intercept is a little bit bigger than 1.5. So I'm going to go with about 1.5, okay? Now let's look at the slope. To estimate the slope, let's find 2 points that are almost on grid lines, and I can see from this point and this point, this is not exactly on grid lines, but they're pretty close. I go up 2 and over 3, so I'm going to say my slope is about 0.67-ish, okay? So if this is my equation was y is equal to 5 times 2 to the x. It said that the slope should be equal to the natural log of the base, natural log of 2. So let's just call up the calculator here. Call up the calculator and type in, come on, turn on. Okay, there we go. The natural log of 2. What do we get? About 0.69. Isn't that about what we approximated? We approximated it as 0.67, and that's because our points weren't exactly on grid lines. Okay, and then our y-intercept, our b, is equal to the natural log of what we're scaling by, which is 5. We're saying this is a little bit bigger than 1.5, so let's see what that one is. The natural log of 5, 1.6. So yeah, as far as estimates go, we were pretty close. Okay, so let's tie that together then and say we've just made a scatter plot of the points x, y, and we've determined that it fits an exponential model. So when we graph the set of points x, natural log of y, here's the equation that we get. We get the natural log of y is equal to natural log of 3 plus x times the natural log of 13. I want to know what is the original exponential function that goes with that set of data. So basically we're just working that thing backwards. So natural log of y is equal to the natural log of 3 plus x times the natural log of 13. So over here on the right hand side, I can condense this down. This natural log of y is equal to, and that will become a product, the natural log of 3 times, I first got to bring this x as the exponent, 13 to the x. Okay, so times 13 to the x. Now notice that the bases are the same, so that means what we're taking the logs of must be the same. So our exponential equation is just simply y is equal to 3 times 13 to the x. And there we go. All done. Okay, in the next one we're going to do some calculator stuff to find, scatter plot, exponential regression, and stuff like that.